In continuation to our discussion on relational algebra, in which we have already studied what is relational algebra, what are traditional set operations in relational algebra, and we have also learned how to prepare queries using traditional set operations of relational algebra. Today we will discuss the next part of relational algebra. The objectives of today's discussion are to elaborate Cartesian product operation, to understand the special relational operations of relational algebra, to prepare relational algebra queries for a given condition using special relational operations. We know that Cartesian product will associate a tuple of a relation with every tuple of another relation, and the resultant relation will contain the number of tuples in relation 1 multiplied by the number of tuples in relation 2. Let us consider that we are given a relation EMP which contains two attributes EMP-NO and name. Basically, it depicts that the EMP-NO 121 has the name Rashmi and 122 has the name Rohit. Let us consider that we have another relation, department relation, named as DEPT. It contains the attribute EMP-NO and department name, and it depicts that the employee number 121 belongs to the computer science department and employee number 122 belongs to the electrical department. Now, suppose that we want to find out all the employee numbers who are in computer science department. If we write the relational algebra expression as select department name is equal to computer parenthesis employee cross department, then this expression will not result in the exact answer. This is because the Cartesian product will give the number of tuples equal to 4, whereas as we have seen in our table, only one tuple should be returned, saying that employee number 121 is in computer science department. The result will be as follows: employee number 121, name Rashmi, department number 121 and department name computer. The first tuple is in fact correct, whereas the another tuple which contains employee number 122, name Rohit, department number 121 and department name computer is not the desired result. Therefore, the Cartesian product expression could not give the desired result, and we will have to modify it. For the exact answer of the query, the relational algebra expression must be modified to this expression, that is select EMP.EMP-NO is equal to department.EMP-NO and department name is equal to computer, followed by the Cartesian product of EMP and department in parenthesis. This expression will not only ensure that the department name is equal to computer, but will also ensure that the result will be derived only if the employee.employee number is equal to department.employee number, and this will give us the correct result, that is the employee number 121 whose particulars are the name is Rashmi. Let us now understand the special relational operations in relational algebra. The first operation we will discuss is set intersection operation, another is natural join operation, followed by division operation. Let us consider the table EMP with the attributes EMP-NO, name and salary, depicting that the employee number 121 has the name Rashmi and gross salary 2200 and so on. Let there be another relation department containing the attributes EMP-NO and department name. Let it be depicting that the employee number 121 is in computer department and so on. Now suppose that we wish to find out all the employees who have salary greater than 2000 and also belong to the Department of Computer Science. Then the expression will be project employee number bracket select salary greater than 2000 followed by the name of relation EMP in parenthesis. Then we will use the set intersection operation followed by the another relational algebra expression containing project employee number bracket select department name is equal to computer followed by the name of the relation department in bracket. Basically, with these two relational algebra expressions, we will get the result containing the employee numbers having salary greater than 2000 and another relation containing the employee numbers whose department name is equal to computer. And upon this we will apply the set intersection operation, which will give us only the employee numbers which have salary greater than 2000 as well as they belong to the Department of Computer Science. And the result will be employee number 121. Its salary is 2200 and he belongs to the Department of Computer Science. Now, if there are two relations R and S, then the intersection of R and S can also be obtained by writing R minus bracket R minus S. Basically, we first perform minus operation on the two relations R and S, and the resultant relation is further subtracted from the relation R. Thus, we can say that set intersection is not a fundamental operation. However, it is easy to perform and understand and therefore used most of the times as compared to the use of minus operation. Natural join operation. As we have seen in the Cartesian product operation, a query not only requires a Cartesian product but also includes a selection on the result of the Cartesian product. That means we always need some equality condition to be put on to the Cartesian product in order to get the desired result. Therefore, instead of using Cartesian product operation, we have another operation, that is natural join operation. The natural join is a binary operation that allows us to combine certain selections and a Cartesian product into one operation. It is denoted by the word join. The natural join forms a Cartesian product of its two arguments, performs a selection forcing equality on the attributes that appear in both the relational schemas, and finally removes the duplicate attributes. Therefore, the equality condition is built into the natural join operation, and also it automatically removes the duplicate attributes. Therefore, it is more beneficial and easy to perform as compared to the Cartesian product operation. Let us say we are given a query to find out the employee numbers and the names of the employees who belong to computer science department. This query can now be easily expressed using the natural join as follows. That is, project, employee number, name, followed by bracket, select, department name is equal to computer, bracket, EMP join department. So first, the EMP join department will be executed, and it will return basically a joint table containing employee number, name, salary and the department name. On this, the selection will be performed with the condition department name is equal to computer, and further on this result, the projection will be performed for the attributes employee number and name. The natural join operation is considered to be central to much of the relational database theory. Basically, it is one of the very important operations which is very essential for the easy query writing. Division operation. The last operation to be discussed is division operation. The division operation is denoted by the divide sign. It is suited to the queries that include the word for all. Let us consider that there are two dummy relations P and Q with their attributes as shown next. Now, if we divide P by Q, the result will contain the attribute A with the values A1, A2, A3 and A5. This is obtained because A1 is associated with B1, so it is there in the resultant relation. A2 is also associated with B1 and therefore it is there in the resultant relation. A3 is also associated with B1 and therefore A3 is also in the resultant relation. A5 is also associated with B1 and therefore it is in the resultant relation. So basically, wherever we have B1, those corresponding A attribute will be listed in the resultant relation. Now consider that P contains the attributes A and B as shown here, and Q contains the attribute B for which there are two values B1 and B2. Now we will see how we will obtain this result by dividing P by Q. That is, we will see first A1 is associated with B1 as well as it is also associated with B2. Therefore, A1 falls in the result. Whereas A2 is associated with B1 but is nowhere associated with B2 and therefore it does not fall in the result. A3 is associated with B1, it is not associated with B2 and therefore it is not in the result. A4 is associated with B2 but is not associated with B1 and therefore again it is not in the result. Whereas A5 is associated with B1 as well as B2 and therefore it falls in the result. Thus, the result will contain only those attribute A values for which B1 and B2 both are associated with A. Now let us consider another example in which the division operation is very useful. Consider a relation product containing the attributes product number and module name, indicating that the product number P1 stands for the module name heap sort. Product number P2 stands for the module name binary search and P3 stands for the module name file manager. let there be another relation developed by containing product number and employee number as its two attributes, indicating that the product number P1 is developed by the employee number 121, P2 is developed by the employee number 122, P3 is developed by the employee number 121, and so on. Now, let us consider that we are given a query to find all employees who developed both the heap sort and binary search modules. That is, we are interested in knowing the employee numbers of those employees who have developed both the heap sort as well as the binary search modules. We will do it partially. First, we will find the product numbers of these two modules and let the resulting relation be temp. That is like this. The product number for heap sort is P1 and for binary search is P2. Thus, the temp relation will contain the information product number P1, P2. And it will be obtained by using the relational algebra expression temp is equal to product number followed by bracket select product name is equal to heap sort or product name is equal to binary search performed on the relation product. So basically we have used the OR operation to combine the two conditions that the product name can be heap sort or it can be binary search. After obtaining temp, we can then obtain the employee number of the employees who are involved in the development of these modules by dividing the relation developed by the relation temp. And the result will be employee number 121 and employee number 122. The result we will obtain is result is equal to developed by divided by temp. Thus what we have done is we have divided the developed by relation by the temp relation to obtain the result. Thus in this discussion we have understood the importance of Cartesian product operation and have also seen what can be the disadvantages of using it. We have learned what are the special relational operations in relational algebra. We have specifically learned the importance of natural join operation and have seen how it has more usefulness as compared to the Cartesian product operation. We have also discussed the set intersection operation and the division operation. That is all for today. Thank you.